All right, everyone. For this week's AI reading seminar, we're looking at a paper that I think will resonate with just about everyone in this room. It's called PaperBanana, Automating Academic Illustration for AI Scientists. Let's just dive right in, shall we? So, take a good look at this system diagram. It's clean, it's clear. It's the kind of thing you'd be proud to put in a NeurIPS submission. Now, I want you to be honest with yourselves. How many late nights wrestling with Illustrator or, dare I say it, PowerPoint, would it take you to produce something that's polished? Yeah, we've all been there. It is a universal pain point in our field. And that really gets to the core of what this paper is all about. We're making these incredible leaps with autonomous AI scientists, systems that can form hypotheses, run experiments, even write code. But then, when it comes time to actually communicate the brilliant results, we just hit a wall. This last mile of visual communication is a massive, time-sucking bottleneck that slows the whole research cycle down. So the author's answer to this problem is a framework they've called PaperBanana. At a high level, what we're looking at is an agentic system. That means it coordinates a whole team of specialized AI agents to take your raw methodology description and just automatically generate these high-quality illustrations. The goal here is pretty simple, to lift this entire burden right off our shoulders. So the key contributions here really boil down to three things. First, you have the framework itself, this whole automated pipeline. Second, and this is absolutely critical for any new research area, they went ahead and created a new benchmark, PaperBananaBench, so we can actually evaluate these kinds of diagrams properly. And third, the punchline. Their results show that this whole approach significantly outperforms the current baselines. Okay, so let's pop the hood and see how this thing actually works. The real magic here is in this multi-agent architecture. It's not just one big monolithic model trying to do everything. Instead, it's a team of specialists, and each one has a very specific job to do. And as you can see from their system diagram, the whole framework is basically split into two big stages. It all starts with what they call a linear planning phase, that's over on the left. This is where all the initial content gets prepped. That's followed by an iterative refinement loop on the right, where the illustration gets progressively polished up. Let's break down each one. Okay, so the whole process kicks off with this linear planning phase. First, a retriever agent goes out and scans a database of existing diagrams to find visually relevant examples. You can think of it as doing a quick visual lit review. Based on what it finds, a planner agent then creates a super detailed, structured description of what the new diagram needs to show. And finally, a stylist agent comes in and refines that plan, injecting aesthetic guidelines to make sure it looks modern and clean. Right, so once that plan is locked in, we move over to the iterative refinement loop. A visualizer agent takes that detailed description and renders the first draft of the image. Then, and this is a really clever part, a critic agent examines that image, finds all the flaws, and gives concrete feedback for how to improve it. It's like an automated peer reviewer. This whole render and critique loop runs for 3 full rounds, making the illustration better and better each time. Of course, a new system is only as good as the way we evaluate it. And to really put their framework to the test, the authors built PaperBananaBench, a brand new benchmark curated from 292 different diagrams, all from recent NeurIPS papers. So it's very relevant to the work we do. Now, quantitative metrics are great. We all love our tables and numbers, but for something as visual as this, a side-by-side comparison can be incredibly telling. So let's take a look at a case study from the paper, where they put PaperBanana head-to-head with a strong baseline model. And wow, this case study really says it all, doesn't it? I mean, the baseline's output on the left is fine, it's functional, but now look at the PaperBanana result on the right. The color palette is so much better. It gets rid of all that redundant text to improve focus, and it even uses these colored zones to clearly separate the different logical parts. It's not just prettier, it is fundamentally easier to understand. And the hard numbers absolutely back this up. This agentic framework gives them a boost across the board. Okay, the gain in faithfulness is a bit modest, but just look at conciseness, a massive 37% improvement. Readability and aesthetics get big bumps too, and it all adds up to a 17% better overall score. That is a very, very strong signal. But for me, this is the real kicker. In blind A/B tests, when they showed the results to actual human researchers, people like us, they preferred the PaperBanana output almost 73% of the time. When the people who actually have to make and read these diagrams overwhelmingly prefer your system, you know you've done something right.
Now, like any really interesting, pioneering work, it's not perfect yet. The authors are refreshingly honest about the current limitations, so let's spend a moment on where this research probably needs to go next.
So they identify 3 big challenges right now. First, the output is a raster image, like a PNG. It's not an editable vector graphic like an SVG, which is what journals really want. Second, relying on a strict style guide makes everything consistent, but it can also stifle creative and diverse designs. And third, it still has some trouble with what they call fine-grained faithfulness.
This quote from the paper really drills down on that third point. The system gets the big picture right most of the time, but it can still mess up the tiny little details. An arrow pointing the wrong way, a line that doesn't quite connect to the box. And what's really interesting is their analysis shows that the critic agent often doesn't even notice these small errors, which suggests it might be a limitation of our current vision models.
So I'll leave you with this final thought to kick off our discussion. This paper presents a really compelling vision for automating a major headache in our work. So let's assume we solve this. That illustration becomes a solved problem. What's next? What's the next creative or communicative bottleneck in our research workflow that we should be pointing these incredibly powerful AI systems at? I'd love to hear what you all think.